Good afternoon, everybody. Thank you for coming to this webinar. My name's Martyn Taylor and I'm the CTO of Bartr Technologies. And today we're going to talk about blockchain technology. So what is a blockchain? How does it work? And what problems is it good at solving? So blockchain just seems to be one of those buzzwords at the moment. It's very in fashion. There's a lot of hype around it and excitement. But unfortunately, the reality of actually what a blockchain is and what problems are they good at solving and how does it work seems to be lost in all of this hype and excitement. There's been several places where this technology has been misapplied. You just have to look at the ICO boom in the 2019, 2018 era to see many examples of that. This resulted in a bunch of waste of resources being invested in this technology and where it's been misapplied into the wrong use cases. So the goal of this talk really is just to give everybody here a good fundamental understanding of what a blockchain is and how it works and what problems it's good at solving. And then hopefully we'll define some vocabulary where we can all have a sensible conversation about blockchain when we're applying this to the 5GZORRO project. So I'd like to start this talk with an anecdotal example. So this is something called a face stone, and this is a historic currency from used by the islanders of a Pacific island called Yap. And obviously the size of these things, they can be 4 meters in diameter. They can weigh several tons in weight. Or they could be as small as a €1 coin or a £1 coin. And the size of the coin, the size of the stone represents its value. Now, for obvious practical reasons, the larger stones weren't moved around very often. So the way that ownership was transferred from one party to another party of these face stones, the islanders used a system where they essentially, the owner of the stone would basically broadcast a message to the rest of the inhabitants of the island, and the rest of the inhabitants would basically keep in their memory a record of who owned which stone and a record of each time that stone had transferred ownership from one party to another party. And this is quite interesting because this system that they use is kind of similar to what we think about as a distributed ledger today, and it has some interesting properties. So first of all, the system is trustless, so there's no single third party. There's no bank or an individual where it sits in between two participating parties. So if two people want to transfer the ownership of this coin, they don't go to this third party. They agree between themselves and then they broadcast the result of the transaction. It's transparent in that everybody on the island has a record of all the transactions that have ever taken place. Everybody on the island knows which stone belongs to who. It's immutable, kind of, in the sense that, oh, we have another participant joined. Apologies for that. Yeah, sorry. So it's immutable in that it's very difficult to change the minds of the people on the island. So once, you'd have to go and try and convince these people, and obviously it's ingrained in their culture, and it's very difficult to make those changes. It's secure, kind of, in the sense that the islanders are aware of the identity of all the other islanders. So if you try to transfer ownership of a coin that you don't own at any point in time, they're just going to ignore you. And it's highly available. So if half of the island was wiped out due to some virus or some pandemic plague or whatever it is, the currency system would actually keep going. The other half of the island would continue storing those records, and transactions could continue to take place. So obviously, in today's world, we don't have physical stones and we're not storing records in people's memories, but what we do have is we have a peer-to-peer network of computers. But the system works very much in the same way, in that you know, any exchange of ownership or value takes place on a distributed ledger. A message is broadcast, but that message, instead of it being broadcast to all of the islanders, it's broadcast to a network of computers, and each one of those network of computers, each one of those nodes in that network, store all of those transactions, and the system as a whole has those same properties. You know, it's trustless, and that there's no central organization managing these transactions. It's immutable, it's secure. We use modern cryptographic techniques to ensure security, and it's highly available. So obviously we're here to talk about blockchain. So what is blockchain? How does that fit into this bigger picture? Well, blockchain is just one type of distributed ledger technology, and I'll touch a little bit later on some of the different types, but I'm not really going to focus much time on that in this talk. It's kind of out of the scope for the session. Okay, so how does a blockchain work? Well, I think the best way to describe how blockchain works is really to look at specific examples of blockchain implementations and look at how blockchain is used to solve specific use cases. And then by digging deep into some of these particular implementations, we can then get to the kind of fundamentals, the core tenets of blockchain technology. And the most natural place to start is with Bitcoin, because that's really where blockchain all started. So I think everybody's aware of Bitcoin, but ultimately Bitcoin is just a peer-to-peer electronic cash system. It allows parties to exchange Bitcoins without any third party. The network itself acts as the trust layer and the storage layer. And in the Bitcoin white paper, the idea of a blockchain, the concept of a blockchain, was outlined as a particular solution to one of the issues that the authors ran into when they were trying to come up with a workable implementation of a peer-to-peer cash system. So we're going to dig deep into Bitcoin. Well, kind of, we'll scratch the surface a little bit and we'll look under the covers in Bitcoin. And then from that, we should be able to get at the fundamental principles of blockchain technology. So before we jump into Bitcoin, I'm just going to do a quick refresher on some cryptographic fundamentals, because these are the key pieces of technology that blockchain is built on top of. So I'll just give you, I'm sure everybody on the call is aware of all or if not most of these, but I'll just do a quick refresher on these cryptographic fundamentals and talk about these properties that these give us. And then from there, we'll build up the picture and we'll see how these are used to enable the Bitcoin cash system, and then you can see how these cryptographic techniques are used fundamentally in blockchain. So there's three principles. We've got public key cryptography, cryptographic hash functions, and signatures, and I'll quickly talk about each of those. So to talk about public key cryptography, I've just first introduced symmetric key cryptography. So for those of you who are not aware, symmetric key cryptography is essentially a mechanism for taking some plain text data that you want to secure, or you don't want anybody else to be able to read it. You take the plain text data and you take something called a key, which is essentially just a string of bits, some arbitrary length. It's not arbitrary length, but some arbitrary set of data. You take those two inputs to a cryptographic encryption algorithm, and then you run that algorithm, and then out the other side you get something called ciphertext. And ciphertext is illegible to anybody that is just looking at it. And the way that you get back to the plain text data is that you use the same key that you used to encrypt the data in the first place. So the key thing here is that in order to encrypt it, you take some plain text and a key, you push it through some function or some algorithm, and out the other side you get some ciphertext. With symmetric key cryptography, in order to reverse that process, you use the same input key that you used during the encryption phase. Now this works perfectly fine, and we use this every day. So if you open a browser session, TLS browser session to your bank, there'll be some negotiation to start off with using public key cryptography, but then ultimately you'll do an exchange where you'll essentially get some symmetric key cryptography, and actually most of the session is likely to be encrypted using symmetrical keys. But there is an issue here with this approach, which is it's very difficult to share these keys. So, okay, if I've got a key and I encrypt some data and I want to send that encrypted data to somebody over a network and I want them to be able to read it on the other side, they also need to have the same key. So how do we share that key? How do we distribute that key? And it turns out to be very difficult using symmetrical keys. So this is kind of where asymmetric key cryptography helps us out. So with asymmetric key cryptography, we have a very similar setup. We have some function that takes some plain text and a key, and it spits out some ciphertext. But instead of when we're trying to reverse that process, instead of using the key that we use to encrypt the data, we actually use a different key. And these two keys are created together, and they're associated with each other, and we call them a key pair. And the interesting thing about these key pairs is that we can apply this various techniques, but one thing that we can do is we could take one of our keys and we can say, right, this is our public key. We'll send it to everybody on the network who we want to be able to secure messages and send them to us. And we can keep one of them private. So if anybody wants to send us a message, they essentially take some plain text, they encrypt it with the public key, the thing that I've just sent out and broadcast to everybody, but only I can decrypt it, right? Because I'm the only person with the private key. Sorry, yeah, and just lastly, the same thing works in reverse, right? So you can encrypt it with your private key, and only the person with the public key is able to decrypt it. Cryptographic hash functions, they're essentially it's a function that has some particular properties. So the first property is that it takes some arbitrary length amount of data. It doesn't matter how long it is. You run it through some function and you'll get a fixed length output. If you change any of the input data, even if it's just one character or one bit, you'll get a totally different output. So it's said to be, random over a certain address space. If you put the same data in twice, you'll always get the same output. And the other interesting feature of interesting property of a cryptographic hash function is that it's something we call a one-way function, i.e. it's very easy, computationally easy, to start with some input text, run it through the hash function and get the output text, the output or the digest. But it's very, very difficult to reverse that process. So it's very, very difficult to start at some fixed known output and then try and figure out what the input to the hash function would have been in order to generate that output. Okay, so what we can do with these two pieces of technology is we can then start layering up some of the techniques in order to give us other properties, right? And one of these techniques is something called the signature. And a cryptographic signature will give us two assertions or two verifications, if you like. So it will verify data integrity. So it enables us to, if it's a sender and a receiver, if they want to transfer data between each other, if there's a signature associated with that message, we can see that the original message hasn't been tampered with, hasn't been changed. And the other thing it gives us is it gives us some sort of identity or some guarantee that the person that generated this message was the owner of a particular key pair. So just quickly look at how cryptographic signatures work. So if we have, for identity, oh, we've got another person join. Okay, sorry about that. Should probably get somebody else to do the admin while I'm presenting. Yeah, so cryptographic signatures. So if we were to use cryptographic signatures to figure out who is the particular owner of a public key, we can do that. First thing we need to do is agree on some text. So up front we decide, right, okay, let's agree on some plain text that we both know about, and we can figure out the details of that later. But the first thing that the owner does to prove that he is the owner of a key pair, or the owner of a private key, is he takes that plain text, he runs it through a hash function, and we've seen that the hash function will then take the arbitrary sized text and it will spit out a fixed length output. The owner of the private key then encrypts it with their private key and then sends the ciphertext over to the verifier. And then all the verifier needs to do to guarantee that he is speaking to the owner of the private key is that he decrypts it with the public key associated with the private key that he's trying to verify. And if he gets the hash back, he then just hashes the original text and compares the two values. If they're both equal, then he knows the person he's talking to is in possession of a private key associated with a particular public key. And therefore, he's verified kind of the identity of that person. Okay, so before we move on, is there any questions on this aspect of the talk? I think it's relatively well known. Okay, good stuff. All right, so I think what we'll do next is we'll jump into the Bitcoin model, and I'll talk about how we start from those cryptographic principles and how we build up to this blockchain technology. So the Bitcoin model has 5 key tenets: addresses, transactions, the blockchain itself, some consensus mechanism in the network. And I'll talk about each of these one by one. So the first thing in Bitcoin, the fundamental unit, or the fundamental object within the Bitcoin network, is something called an address. And all an address is it's some number that allows an owner of some Bitcoins to send Bitcoins to another owner, right? So and each of those owners, they possess an address, and that's the thing that they share with each other. So you can kind of think of an address in Bitcoin as like an international bank account number. Anybody that you want to send you Bitcoins, you broadcast your address to those people, and they can send Bitcoins to your address. So what is an address in Bitcoin? Well, all an address is a hash of a public key. Okay, so to participate in the Bitcoin network, first thing you need to do is you need to generate a key pair. So you generate your key pair, you have your private key and you have your public key, like we've just discussed. Keep my private key private because that's going to give me access to all of the Bitcoins associated with my address. I then hash it, and the result of that hash is my address. That's the number that comes out at the end. That's the thing that we share and we see when we open up our Bitcoin wallets and so on and so forth. So, okay, so we have an address, and we've had people send us money or Bitcoin to our address. How do we prove that we are the owner of that address, so that we can then spend the Bitcoins that are associated with that address? And the way that happens in Bitcoin is that the owner of an address, when they claim ownership, so whenever they want to spend some Bitcoins, you have to prove that you are the owner of the address, and you need to provide two pieces of information. So the owner provides, first of all, the public key, associated with that address, and a signature. So then any verifier that's verifying that the Bitcoins that have been requested to be spent on a network are actually owned by the person who is claiming to own this address. They look at, first of all, they look at the public key and they say, okay, well, is this the public key that's associated with the address? Well, that's quite easy to figure out. We can run it through this process. We take the public key, we run it through the hashing algorithm, and then if the result is the same as the address that's associated with the Bitcoins, then we know that this was the public key. And then we take a signature. So the owner signs something. We can talk about the details of the signature later, but the owner signs something with a private key, and then using that same technique we spoke about earlier for verifying signatures, any verifier just needs to take the public key, decrypt the signature, and then make some comparisons with the resultant text. And if that's all hunky-dory, everything's right, then we know that this is the person that has the private key that's associated with this address. So a thing to note here, which is quite important, is that at least with Bitcoin and with a lot of other blockchain technologies, there's no concept of identity in terms of an organization or an individual. The identity is purely at the address level. So the only thing that you can verify is that the person who's interacting with for a particular transaction has the private key that's associated with an address. That's the only thing. So the whole identity mechanism, the whole way of transacting between parties is purely just based on addresses and private keys. So the next fundamental unit in blockchain is something called a transaction. And a transaction is simply just one way to transfer Bitcoins from one address to another address. I'm talking purely just in terms of Bitcoin right now. And a transaction in Bitcoin is quite interesting, the way that transactions work. So if any owner of any Bitcoin wants to transfer Bitcoins from one address to another address, so you went to the pizza shop and you've bought a pizza and you want to pay the owner of the pizza shop, what needs to happen under the covers is that we need to create something called a transaction. And transactions in Bitcoin they have three pieces of information. So they have the inputs to the transaction. And you can kind of think of the inputs of the transaction as the state before the transaction happened. And then you have the outputs of a transaction, and that's the state that I would like to have these Bitcoins in after the transaction has happened. Only the owner of any Bitcoins is allowed to have Bitcoins, is allowed to spend those Bitcoins within a transaction. And the way that the way that an owner can provide proof that is the owner of these Bitcoins is it comes back to providing those two pieces of information I talked about earlier, which is the public key and the signature. So you can see by just using the technique that we talked about earlier, we've got on the left-hand side here, we've got this 2 Bitcoins in red. And each Bitcoin has the current owner's address associated with it. And that current owner has provided the public key and the signature. So any verifier of this transaction basically follows that step. They run the public key through the hashing algorithm and compare the result of that to the address that's associated with this Bitcoin. And then they use the signature to verify that actually the person that's created this transaction is in possession of the private key that's associated with that address. And on the right-hand side here, we have the new owner, and we have something called change. Now, with Bitcoin, the granularity of the Bitcoin isn't necessarily fixed it's arbitrary. It depends on the history of what's happened previously. So you can kind of think of Bitcoin's a bit like paper notes. So if I go in my wallet and I say, right, okay, I've got a £5 note or a €5 note and a €10 note, and I want to go and buy pizza for €9, well, that's a bad example, for €12, I need to go in my wallet and I need to take out the £10 note and I need to take out the £5 note, and I give that to the shopkeeper, and then the shopkeeper gives me £3 change. And that's very similar to how Bitcoin works. So on the left-hand side here, you can see we've created a transaction and we've used, you know, we've got one entry with something which has a value of 4 Bitcoins, another entry which has a value of 2 Bitcoins. I'm going to pay the owner 5 Bitcoins, and then I'm going to send the change back to myself. So one of the interesting properties of Bitcoin is that the inputs and the outputs need to be the same. Otherwise, you know, the value just disappears into thin air. Well, it goes to the miner, but it's kind of a detail. And like I mentioned earlier, the inputs to a transaction it can be thought of as the state of those Bitcoins before the transaction happened. And then the output is the state that the owner of the transaction wants those Bitcoins to be in after the transaction has happened. So you can imagine that the input is simply just stating the current owner, and the output is stating the new owner. So you can take these inputs and outputs and you can chain them together. So the input of one transaction is the current owner. The output of the transaction is the new owner. And then that new owner can then take the output of that previous transaction as an input to a new transaction. And this kind of chain follows on. So you have on the left-hand side here, so we have the owner 111 in blue is transferred ownership to the owner in red 222. And then when that second owner, the red owner, wants to create a new transaction to spend those Bitcoins, he simply just refers to the output of the previous transaction, which states that he is the current owner. And he uses that to spend his Bitcoins, and then he transfers ownership from one to the purple owner, who does exactly the same thing when he creates a new transaction. He's just referring to the fact that this Bitcoin was transferred to him. So you can kind of think, again, coming back to the paper money analogy, if we have a £5 note, and it starts off on the left-hand side here, the owner is 111 is essentially giving this £5 note to the red owner at 222. That red owner is taking the same £5 note and he's passing it on to the purple owner. And that purple owner is taking the same £5 note and he's passing it on to the green owner. And the person stood at the end of this chain of transactions, the person holding the £5 note, that's the person that currently has the rights to spend those Bitcoins. So this is why this particular transaction model is something called the unspent transaction output model, because Bitcoins are really represented by the last transaction output, i.e. the transaction output that hasn't currently been spent in another transaction output. So there are other models, transactional models, but this is the one that Bitcoin uses. So this is great. So what this essentially gives us is it gives us a cryptographically secure technique to transfer ownership of value across multiple parties. And there's no way, it's very difficult and almost impossible to be able to spend Bitcoins that you don't own, because it's based on fundamental cryptographic techniques using those public key cryptography things that we talked about earlier on. So it's a very nice, elegant solution for transferring ownership and for the ability to see which Bitcoins you own at any one point in time and who has the rights to spend them. But unfortunately, that doesn't solve the whole problem. And in the Bitcoin white paper, it talks about something called double spending problem. And the double spending problem is essentially this. So with a centralized system, if Alice tries to take some value, let's say they have £10 in their bank account, and they try to spend that £10 twice, the central organization, like a bank, for instance, in this case, is going to take those two requests to transfer the £10 to two separate entities, and it's going to order them. It's going to deal with one of them at a time. So the first thing it's going to do is say, okay, Alice has tried to spend £10, transfer £10 to Bob, so I'm going to follow my procedure. So I'm going to say, right, okay, does Alice have £10 in her bank account? First of all, yes, she does. Okay, great. So first of all, I'll debit Alice's account by £10, and then I'll credit Bob's account by £10. And that those series of steps are atomic, so they can't be broken down. When Alice sends the next request to transfer £10 to Charlie, the bank just follows the same process again, because it's dealing with one transaction at a time. But this time it sees that Alice's account has already been debited by £10. It's currently zero. So Alice doesn't have the funds, so the bank just rejects the second request to transfer money. Now, it turns out that this problem is very difficult to solve in a decentralized system because we don't have that single point, the single third party that sits in the way, that takes all of these requests for transactions and orders them and deals with them one by one and applies the logical steps, let's check the account has the appropriate balance and so on and so forth. And we can actually see that even with a cryptographically secure mechanism for transferring value, like we've just described based on those techniques, it's actually possible for Alice to double spend her money. So Alice could perfectly reasonable for Alice to create two transactions and transfer ownership of £10 or 10 Bitcoins or whatever it is to Bob, first of all. Bob can look at that transaction and he can say, right, okay, let me verify that, and he can follow all of the steps that we spoke about earlier. So, is the public key associated with the address? Yes, it is. Okay. Is the signature valid for that public key? Yes. Okay, now I can guarantee that Alice is actually the owner of these Bitcoins, and the person that's created this transaction is Alice. So as far as Bob is concerned, this is a perfectly valid transaction. So in his global view, he's perfectly happy to accept that as a payment for the service that he's providing. Now, Alice could do the exact same thing and send the transaction elsewhere. So as far as Charlie's concerned, in this case, Charlie followed the same steps as Bob and notices, public key's fine, the signature's fine, these Bitcoins are owned by Alice, the transaction looks good to me. So Alice has successfully managed to double spend her money. So how does Bitcoin solve this problem? In the Bitcoin white paper, it outlines an approach to fixing this issue. So this is an issue that's it's been around for a long time, this double spending problem, particularly in the peer-to-peer cash systems. They've always struggled with solving this problem. So Bitcoin's novel approach was to develop, in its words, a peer-to-peer distributed timestamp server. And what that does is it guarantees the chronological order of transactions. Once you've got the chronological order of transactions agreed across all of the participants in the peer-to-peer system, you can then work through those transactions one by one, and you can figure out which transactions are valid and which transactions aren't valid. If we just go back to the previous example, if we were to try and resolve this issue, after the fact that it's happened, whose transaction would we reverse, right? Because Bob would say, well, no, my transaction is valid, and Charlie would say, well, okay, well, my transaction is valid. There's no way here to say, okay, well, Bob, you were first, so we're going to go with you, Bob, and Charlie, unfortunately, you've missed out this time. So yeah, this is kind of the novel thing that Bitcoin introduced. And the way that Bitcoin does this, it does it in two parts to this timestamp server. And the first part is something called a blockchain. And what the blockchain does is it gives us that chronological ordering guarantee. So it enables us to reason about the transaction ordering. So we can see that within the blockchain, within each block, there is a group of transactions. And the transactions within a single block are ordered. So we can, first of all, we can reason within a single block. We can say, okay, if Alice tries to do a double spend in transaction 1 and transaction 2 here, anybody that has this block will be able to see, okay, well, transaction 2 came after transaction 1, so therefore transaction 2 is not valid. And then the next step is that there's a chronological ordering between blocks. So all the transactions in block 3 happen chronologically after all the transactions in block 2, and all the transactions in block 4 happen chronologically after all the blocks in block 3. And the way that these things are linked together is by essentially taking a hash of a previous block. So the way that block 3 is associated to block 2 is that when the block 3 is generated, the generator of block 3 would say, okay, this is next in the sequence to block 2. Here's my reference to block 2. It's basically take the data associated with block 2, run it through a hash sequence, and then I'll include that in block 3. And that's how we have this kind of backward linking mechanism where each block refers to the previous block. And this linking mechanism essentially results in something that looks like a chain, and hence the name blockchain. Now, like I mentioned, this gives us chronological ordering, but it's not particularly very secure. Why? Because somebody could easily come and tamper with this, right? So they could say, right, well, I was Alice and I spent some money in block 1 or block 2. In transaction 1, I went to the shop and I bought pizza. But later on, I think, you know what, I don't want to pay for that pizza anymore. So what I'm going to do is I'm going to go back and I'm just going to delete the transaction from block 2, pretend it never happened, and then modify the block, and nobody has any reference to that transaction anymore. Well, that would cause an issue, first of all, because block 3 refers to block 2, and by changing the data, by removing the transaction from block 2, what we're actually doing is changing the result of the hash. Remember earlier we talked about a small change in the input data to a hash function gives you a totally different digest. So that would break the linking here. So the link between block 2 and 3 and block 2 and block 3 would be broken because that data has changed. So block 3's hash function no longer refers to block 2 anymore. Okay, well, that's fine. An attacker could easily get around that by saying, okay, well, I'll just regenerate the hash for block 3 and I'll make a point to my compromised block, which they could perfectly easy to do. We said that it's very, very easy to take some input to a hash function and get the output, so it's not necessarily computationally expensive. But obviously that would break block 3. That would break the linking from block 4 to block 3. So then the attacker would then need to update the hash in block 4 and so on and so forth, and repeat this several times. Now, because hash functions are not necessarily difficult to change, an attacker could quite easily remove the transaction from block 2 and then just modify all the blocks after it, so they all point to this compromised block and job's done. So how does Bitcoin propose to prevent this sort of issue? And essentially the way that it does this is by introducing some arbitrary computational work or some difficulty in generating some of these blocks. So we talked about, hash functions are quite easy to create. The gathering of the transactions and the processing them into some sort of data object, that's very easy to do. But if we had some kind of arbitrary difficulty in generating one of these blocks, then it makes it hard for an attacker to come and say, right, okay, well, I'm going to change this block because there's now some difficulty associated with it. And that's what this difficulty is, something that we call proof of work. So proof of work is essentially a mechanism for coming to consensus based on how much work has been put into generating blocks, right? So if we make this really difficult to try and to generate one of these blocks, it then makes it very difficult for an attacker to change that one block. But obviously, like we mentioned earlier, in order to change one block, we have to change subsequent blocks so they point to the previous block. And if this difficulty, this arbitrary amount of work, happens for every single block along a chain, the longer that chain is, the harder it is for an attacker to modify. So the further you are away from the end of the chain, the more secure you are. And this proof of work mechanism it comes back to our hash function again. All the any node that wants to verify all of the transactions and propose a new block does is they take a bunch of transactions, they group them all together, they then run the resultant object through a hash function, and they check that the hash function starts with a certain number of zeros. Now, because another property of a hash function is that it's totally random across an address space, this trying to find the result of a hash function that starts with a certain number of zeros is essentially random as well. And again, coming back to another property of hash functions being that it's very difficult to work from the digest and work backwards. It means that the only way to approach this problem is just by taking the block, running it through the hash function, checking to see if it starts with a certain number of zeros. If it doesn't, we modify the block very slightly. So the input data to the hash function changes, and then we check the output again. And we just keep repeating this process until randomly we stumble upon a block that has this correct number of zeros at the beginning. And once it does have that, we say it's valid. So the way that we tinker with the input data to the hash function is essentially by changing a number that's associated with a block. So a verifier of transactions who wants to propose a new block to the network, they gather all of the transactions, they create the SHA-256 that points to the previous block, and then they essentially just sit and play with this nonce, this number, use only once number, and keep running it through these hash functions until they eventually come up with a number that satisfies this requisite. Once they do that, they propose that block to the network, and then other nodes can very easily repeat the process. So they can take this this block that's been generated, run it through the SHA-256 and check that, see if it starts with these numbers. If it does, great, it's a valid block and we'll accept it. If it doesn't, then we throw it away. So what's happening on the network and blockchain is that because it's a distributed system, because these blocks are constantly being generated, we have something called forks. And a fork is essentially when more than one person on the network has proposed a new block that is perfectly valid. All the transactions are valid. So, every verifier will verify there's no double spends in that transaction and that they conform to the, the cryptographic signature and principles that we spoke about earlier. They'll check that the block data as a whole, once they run it through the SHA-256, comes out with the appropriate number that the network has decided, that beginning number of zeros. So there's quite legitimately at any point in time, there's all of these valid blocks being thrown around. And each block might have the same transactions in. It might have some transactions in that are the same as the other transactions. It might reorder things. So, if Alice does try to double spend her 10 Bitcoins, some nodes on the network might have gathered the transaction to Bob and put that into a block first and sent that out. Other transactions might have seen the one from Charlie first, just due to latency in the network, and put that one in the block first. So we've kind of constantly got these perfectly valid blocks floating around the network. So the next question is, how does the system, how does the network as a whole come to some consensus? How do we all agree on the state of the system at any point in time? And the way that Bitcoin does this is that the consensus algorithm always moves towards the longest chain. So the longest chain being the most number of blocks, which represents the most amount of computational power that's been put into generating that chain. So like we mentioned earlier, there's an arbitrary difficulty for each block. So 2 blocks, there's obviously twice the difficulty as 1 block. 3 blocks is 3 times the difficulty as 1 block, and so on and so forth. So the network always converges on the longest chain because that's had the most amount of effort put into it. And the longer this chain is, the harder it is for an attacker to modify it or to change things earlier on in the chain. So if an attacker try to change, this green block here, they would need to change the red block, and they would need to change the orange block. If an attacker wanted to modify this blue block at the bottom, it only needs to modify the blue block. So then we ask ourselves a question then, how do we know as a participant in this network, when is the transaction safe, right? Or we call this thing finality in the blockchain world. So if I create a transaction, or somebody sends some Bitcoins to me, and I see that it's been added to a block, and I see that the block has been validated, it's been mined. When is it safe for me to release the goods, right? So somebody's just purchased a high-end laptop from me for 3,000 Bitcoins, or maybe it's not that many, 1 Bitcoin. When should I release these goods? Because, like I mentioned earlier, it could be, quite acceptable that, first of all, the block that I can see that transaction in, that might be accepted by the network. It might have been validated, but a bunch of other blocks might come down the line a little bit later on in time on a different chain, and that chain ends up being the longest chain. And the transaction that I can see in this block, that no longer becomes the source of truth, or the agreed upon number of blocks in the network. So you can have a situation where, as a participant in the network, I take a look at all of the blocks that have been mined, and I can see, the transaction that Bitcoin was sent to me, that's in a block, it's been mined, and it's currently in the longest chain, right? So it could be that this transaction is in this orange chain here, but due to latency in the network and the distributed nature of peer-to-peer systems, there might be another 10 blocks out there that come down the line and make a longer chain along this bottom here. And none of those blocks might have my transaction involved, included in it. So with blockchain right now, there's no 100% sure way to know that your transaction is going to land, is going to be decided upon the network as the single source of truth, because there's always a small possibility that other blocks in the network are out there, they just haven't landed on us yet. And even though we're currently in the longest chain, another chain might get formed, which is much longer, and the network might move towards that chain. So with Bitcoin, usually the finality period is around about 6-7 blocks. So if your transaction is in a chain that's 6 or 7 blocks longer than the rest of the chains that you can see, then the probability is that it's very, very unlikely that there's other blocks in the network that are going to come out and supersede your longest chain. But still, fundamentally, there isn't 100% guarantee. There's always that chance that another chain could be out in the network and the ether come along and supersede your chain. So something important to take away from this is that it's probabilistic. Obviously, the last thing in the blockchain, as blockchain tenants, is something called a network, and the network is essentially just a bunch of nodes that are all connected together, all contributing to this system. So with blockchain, we have two types of actors into the system. We have, peers. Sorry. You have, users that are trying to transact value from between one another. Then you have the network itself, which is constantly doing all of this verification and passing blocks around and ensuring that transactions are valid, that they all conform to the cryptographic techniques and all of that kind of good stuff. And each one of these nodes in the network, we refer to these as miners. And each time a miner finds a valid block and that valid block makes it into the longest chain, they are rewarded in some way. So they get some Bitcoins for doing that. Okay, so Bitcoin model recap. We talked about 5 things. So we talked about addresses, transactions, blockchains, consensus, and the network. So a few takeaway things, and just a reminder here. So address is obviously the core unit for passing around to identify participants. There's no physical identity associated with that person other than just the hash of a public key. So it's totally arbitrary and anonymous. I think in 5GZORRO, the likelihood is that we're going to have some sort of identity, because in a business-to-business relationship, there generally needs to be some identity for doing things like due diligence and so on and so forth. So something that we need to consider: how do we add identity into whatever architecture that we use? We've talked about transactions as being the thing that is used to transfer value in Bitcoin. Now, I mentioned transferring value, but what I also talked about was really what transactions are doing is they are defining the state of the system before the transaction and the state of the system after a transaction. So you can think generically of transactions as state transitions. So we have this kind of event-sourced sort of model where we have all of these state transitions being sent around the network. And when everybody agrees on a fixed set of state transitions, transactions within blocks and the chain and so on and so forth, you can then use all of those state transitions to build up a global picture, right? So if you have, your Bitcoin wallet is essentially just an application that does exactly that. It's just looking for all of the state transitions for all of the Bitcoins that you are associated with. It's then building up a global view of all of the state transitions for those Bitcoins. So your wallet will say, okay, there's 100 transactions associated with your address. These are the 10 unspent transaction outputs that are associated with your address, and the total value of all of those 10 is 50 Bitcoins. And that's the balance that gets shown in your Bitcoin wallet. So all the Bitcoin wallet is doing is just looking into the network, looking into those transactions and figuring out which ones are associated with you, and then using those state transitions to build up a global view at any single point in time. We have the blockchain component. And like I mentioned earlier, the blockchain component really is just giving us that that chronological ordering of transactions. It's not giving us anything other than that. And there are several other ways that you can achieve the same thing without using a blockchain. So there's a couple of projects that use other techniques. So there's a project called Tangle. Instead of using blockchain, Tangle used something called a directed acyclic graph, which basically means that transactions are associated with each other, and they essentially create this one-way graph. There is some more research around Hashgraph, which is some proprietary software that works in a similar way to the distributed acyclic graph, but it's proprietary software, unfortunately. But essentially, fundamentally, there's nothing really like intrinsic or special about the actual blockchain per se. It's grouping all of these things together and bringing them all together to solve, particular use cases. So you can't have, without the transactions and the addresses and the consensus mechanisms and everything else, blockchain by itself doesn't really offer you much other than that chronological and ordering. We looked at a consensus mechanism based on proof of work, which is, like I mentioned earlier, it's a way to add some arbitrary effort into generation of blocks, essentially to do a couple of things: slow down the network, so the network can eventually converge, but also to prevent attackers from modifying blocks and adding and removing and manipulating transactions. There are several other consensus mechanisms, and I think we probably need to have a discussion at some point, maybe in the new year, about the correct way to approach this. So obviously Bitcoin is a public network, which means that it's open to all participants, and many of those actors could be bad actors. I think in 5GZORRO we can maybe relax some of those trust issues with a trade-off to add some sort of scalability advantages. And then we've obviously got the last thing is the network, and the network being all of those peers that are communicating. And there's a bunch of different ways that we can configure our network. So we can have a public network such as Bitcoin, where anybody can join. I think in 5GZORRO, probably what we want to do is have some sort of private permission-based network where we have participants, access is restricted to only certain participants, and then within that private network, each participant might not have the same rights. So we might have some participants that are able to read only, for example, and other participants that might be able to write new transactions to the network. So these are all.
Sorry, it's Gino speaking. Just a question. So are you advancing the slides? Because I see always the same picture projected. I'm not sure whether you are referring to specific things which are not projected now. I see address, transaction, blockchain, consensus, and network only. So the recap model.
No. I'm on the same slide.
Okay.
Yeah.
Just wanted to be sure that actually what you were now basically describing was not basically part of subsequent slides we were.
Yeah. So I think I've got some more slides. I'm gonna talk about some other one other feature which is important, but I think these are the questions. So each blockchain has each blockchain technology has either the ability or a difference in the way that each of these components work. The question is, when we're architecting a new blockchain network or DLT network, is what are the bits and pieces that we need from each of these? So how do we configure the consensus component? What data is going to be stored within the transactions? How many transactions per second do we need to be able to process? These are all the questions that we need to ask ourselves when we start getting together and thinking about, what does this network look like? That's kind of beyond the scope of this talk, because obviously we're just talking about the fundamentals here. So my suggestion is that in the new year we start digging into each one of these topics, and we start mapping those back to the use cases. So once we've got the use cases and the requirements analysis from that, we can then kind of get an idea of, you know, what are going to be the requirements on the system, and then from that we can start making decisions on what particular pieces of technology do we use for each one of these. Okay, so lastly, before we end, there's one other important thing to cover, and it's something called smart contracts. So again, following on from blockchain, what I'll do is talk about smart contracts with respect to Ethereum. So Ethereum is another blockchain project. There's two parts to the Ethereum. There's the open source Ethereum community with open source technologies, where you can take the Ethereum technology and you can apply it in your own network. But I think probably what most people have probably heard about here is the public deployment of Ethereum. And Ethereum is quite interesting. So on the back of Bitcoin and the back of the success of Bitcoin, a lot of new projects started springing up, which were not necessarily associated with e-currency, but were trying to use the same kind of techniques and the same approach that Bitcoin used for e-currency, but applying it in different use cases. So there's a few early projects, Namecoin for one, which is kind of trying to do some sort of like naming service. There's a bunch of other projects. And essentially what these projects were doing is they were taking the Bitcoin source code and they were trying to modify it in a way that was specific to their use case. And what Vitaly Buterin and the guys at the Ethereum Foundation were interested in was, all of these new potentially interesting ways of solving problems that was pre-Bitcoin wasn't possible. So what they wanted to do was develop a generic platform that was based on the fundamental principles of blockchain, by using all of those things that we've just talked about for transferring value, but do it in a way that was configurable, and that application developers could come and implement their own use cases on top of that. And that's kind of why Ethereum was born. So Ethereum introduced this idea of something called smart contracts. Well, they didn't introduce the idea of smart contracts. Smart contracts have been around for a while, but what they wanted to do was introduce this idea of being able to execute arbitrary code, but within the blockchain environment. And by doing that, it enabled application developers to build a whole plethora of applications that were associated with a transfer of value and have the distributed nature of the blockchain. So what is a smart contract, you ask? Well, there's a bunch of different definitions online, and most of those definitions refer back to some sort of legality or some sort of way to create a digital version of a legal contract. And I think initially, in the early days of Ethereum, that was the case, that they were really trying to replicate a legal contract. But it became something a lot more general. So my definition of a smart contract in the context of blockchain is basically just any computer code that is stored and or executed on top of a blockchain network. It doesn't necessarily need to be associated with a legal contract. Okay, so very quickly, how does this work in Ethereum? Well, we've talked about this model in Bitcoin, this UTXO model, the unspent transaction output model, which has this idea of Bitcoins, which was kind of, I use the analogy of paper money, right? Where we pass this paper money around, and then the person holding the piece of paper at the end of the chain is the person with the rights to spend it. except it's a little bit more advanced than that, in that there's a record of every time that piece of paper exchanged ownership. But ultimately, in order to see how much money you have in the network, or how much value you have in the network, you need a separate application that is keeping track of all of these transaction outputs and is pulling them all together and giving you some sort of balance at the end of it. And then you can interact in that wallet application, can then help you spend those by creating those transaction objects that we described earlier. The Ethereum account model, and I'm using Ethereum here just because it was the first real stab at using of creating a fully Turing complete scripting or smart contract language, is slightly different in that actually an account is a first-class citizen in the Ethereum network. So your address in Ethereum, you still have an address, but that address actually has some sort of physical thing associated with it, and that's an account. And you can think of an account just like a bank account, where you have a balance in your bank account, and in order to transfer value from one bank account to another bank account, we just essentially create a transaction, and one of those accounts is debited and the other one is credited. So it's a different transaction model to Bitcoin. And the way that the Ethereum nodes keep track of everything that's happening in the network is that they have two things that they're tracking. So first of all, they have all of the transactions, and we mentioned earlier that you can think of a transaction a bit like a state transition, where you're just moving from one global state to another global state. So each node in the network is essentially keeping track of all those transactions and then applying each state transition to its global state. So it's got a record of right now, this is what the current state of the network is, as far as I can see, and here's all the data that backs it up. So again, it's very similar to the event-sourced architecture. Sorry, so just one other thing on this is that in Ethereum there are two different types of accounts. So now that we have the concept of an account, this is why I wanted to explain this. There's two types of accounts. There's something called an externally owned account. An externally owned account is a bit like your Bitcoin wallet, right? So it's a bit like end users interacting with the system in order to invoke some function or to transfer some value or whatever it is that they're trying to do. And there's something called a smart contract account. And that smart contract account has some code associated with it. So if you want to create a transaction to a smart contract account, you can send a transaction to that smart contract's address. So each smart contract will get its own address when it's created. And within that transaction object, there is some data that tells the smart contract to execute. So what does a smart contract look like? So within Ethereum, there's something called the Ethereum virtual machine, and the Ethereum virtual machine is essentially just a set of operational codes, just like CPU opcodes, right? Except that there are some restrictions there, and I'll talk about those restrictions and the reason why they're there in a second. But this is a smart contract I wrote a couple of weeks ago. It's just very, very simple, just for an example. So this smart contract represents some sort of spectrum asset. And it has two fields. The first field is the current owner of that asset, and the second field is the ID of that asset. It's very, very simple smart contract. If you look at the constructor component of this smart contract, what this is essentially saying is when the smart contract is first created, I need to pass in an ID. And that ID is set in the asset ID. And then what I'm going to do is I'm going to take the owner, the initial owner of this asset that's represented on the blockchain, and I'm going to set that to the person that created this this smart contract. So very naive implementation for the purposes of this demo. There's one function on this smart contract, and basically all that function does is it transfers the ownership of the asset from one owner to another owner. So we do a quick check. We say, okay, is the person that's calling this function, first of all, are they the owner of this asset? If they are, then they currently have the right to change the ownership. And then we set the owner to the new owner that's been passed in as part of this transfer function. This is written in something called Solidity, and Solidity is kind of just a high-level language that compiles down to the EVM. Okay, so coming back to smart contract accounts. So I mentioned earlier that we have these special accounts called smart contracts, and each of these smart contract accounts has some code associated with them. So for a developer to deploy some smart contract, basically all they do is they take the smart contract code, they compile it down into the format that the Ethereum network requires, and they send it to a special address. So they create a new transaction, just like you would create a Bitcoin transaction, and you say, right, I want to transfer these Bitcoins from this party to this party, except that the developer is here, he's taking his contract and he's saying, right, I'm going to create a transaction, and that transaction is going to get sent to this special address in the Ethereum network. And what that special address does is it takes the code, it deploys it onto the network, and then it allocates a new address for that smart contract. So you can think of this as a bit like a URL on the web, right? So if you wanted to do a REST call to some service that's running on the web somewhere, you need to have the address of that service, and the address that's sent back from the Ethereum network is the address that the developer will then use to interact with that piece of code going forward. And all the network does is it takes that smart contract, it's just wrapped up in a transaction like it would have been. All of the data is still sent around using transactions, except there's a transaction that says the state before is that there wasn't a smart contract, and the state after is that there's this new smart contract, and this is its address. And everybody in the network, when they receive that new transaction, they update their global state to show a new account with the owner of that account, and then store the code that's associated with it. So how do we invoke a smart contract? So to invoke a smart contract, all the developer does is he sends another transaction, but this time the address of that transaction is to the smart contract address. And within that transaction, you can add some data, and within that data, essentially, there's a function call, and that function call basically has the signature of the method and any inputs to that function. Again, what happens in the network when this new transaction is created is obviously the transaction gets sent around, everybody agrees on it, and then everybody in the network unpacks the function call, executes the code, and then updates its global state. So the code is executed. The result of that is now the new global state of the network. And I think that a key takeaway here is that with Ethereum and with various other implementations of this, every node that's participating as a full node in the network is going to execute that code. So it's not like the code is executed once and then the final state of the application at any one point in time is then distributed across the network, which is kind of more the traditional approach of doing something like this. Everybody in the whole network has their own global state, and everybody in the network, once they receive that transaction, are going to execute that code on their local machine. So you can see, for obvious reasons, this doesn't scale very well. Another takeaway here is that because everybody is executing this independently, it's very important that the code that's being executed is idempotent, which means that you know, if we have the node on the left-hand side here, if he executes the code, the state of the global state of the system at any point in time must be exactly the same as when node 2 and node 3 executed. Otherwise, they're going to get different views of the world and the whole system is going to get out of sync. So for this reason, Ethereum has created a very limited execution environment. And within that execution environment, there are certain things that you can't do. So anything that adds some randomness into the execution path is going to, obviously, it's going to create some differences between the resultant global state. So there's no mechanism, for example, in Ethereum to generate a random number. And you know, all of the control flow needs to be fixed in order for everybody to get to the global state. And the other thing that's happening here is that there's no network access. So the only data that a smart contract can access is data that's already on the blockchain, for obvious reasons, right? Because due to latency, the geographical differences between parties when they're executing this smart contract code, you know, if the node on the left calls out to some third-party service and says, look, give me the FX rate for US dollars to euros, right? Because I'm going to make some calculation and I'm going to save the results. By the time that the node on the right has executed the same code, when he calls out, the FX rate has changed, right? So there's potential here for him to get out of sync. So there's no network access. You can't access any data that isn't already on the Ethereum blockchain. And that kind of causes a problem in real world scenarios, because in the world, really what we want to do is we want to act on real world data, right? And in 5GZORRO, we need to be able to see outside of the network. We need to be able to see, you know, what are what's the telemetry data that's being captured for these services, so we can enforce our SLAs, for example. And a common approach to do this is to use something called a smart contract oracle. And basically what all of the smart contract oracle is a gateway between the blockchain and the outside world. And the way that it works is that smart contracts can interact with these oracles. All they are is essentially smart contracts that are written, that are deployed onto the network with some external process that's monitoring the logs of the network. So any smart contract that we write and we say, look, we need an FX rate for US dollars to euro. We need you to tell me what that is. And all the oracle is going to do is it's going to take the request from the smart contract. It's then going to go out to some third-party service and say, right, what's the exchange rate? Okay, it's euros, it's whatever, 1.1. It then takes the result of that external call and it writes it within a transaction on the blockchain. And once it's written within a transaction on the blockchain, at that point it's immutable. And at that point, smart contracts can then start reasoning about that data because it's on the blockchain, it can't change. So everybody in the network is going to be able to see that same data. So they're all going to come to the same conclusion when they've executed that code that's within the smart contract. Oracles also help us with other things. So as well as just external data feeds, they can also integrate with external services. So for example, if we wanted to add some sort of payment mechanism for settlement of services, we can set up an oracle that acts as a gateway between something like the blockchain and Swift for banking, right? Or whatever service it is. It can also be used for, I think we talked about in the report, sorry, the proposal, about using oracles for sitting in between a T, so taking the results of it, the trusted execution environment, that's processing all of this telemetry data, taking the results of that aggregated data and posting it on chain. But essentially, yeah, due to the nature of smart contracts and the way that they work, we need this way to ensure immutability and ensure the idempotency of the contract code. And smart contracts give us that. Smart contract oracles give us that that ability. Okay, so that's the kind of the last thing to complete the picture. We've talked about addresses, transactions, blockchains, consensus, network, and smart contracts. I think the next step from here is to start digging into each one of these one by one, and we can either do that on a call, or we can start pulling together a document, maybe after we get the results of the requirements analysis, and we can start investigating the various different technologies and the trade-offs, the pros and the cons of each one of these components. And then by the end of that, we should be able to pull this together and get a picture of what we really need out of this DLT layer. Okay, that's it for this talk. Just the fundamentals. If we want in the new year, we could start looking into. I could do another talk where I can talk about the various options for each of these. But it's a bit out of the scope for today's session. Anybody
Martyn,
have any questions?
It's Gino speaking. So two questions actually. So the first one is more than a question, is an action. So if you can basically put the slides on Confluence somewhere into I don't know, the proper place, even outside of the work packages. I'll try to create a a tech area or something like that where we can bring in useful material, and then basically we'll put in there all this stuff. Second, if you can also complement these slides with some references to good books or primers or whatever, which you deem could be a useful read for the starter. Because one thing would be to run again the recorded webinar. Another thing would be to go a bit more in depth. So what you would recommend to study for this? Sure. And final request is about basically the exit tools that can be used. I've seen basically Ethereum mentioned in this, related to basically the type of technologies that you deem are good candidates for Zorro at the moment to evaluate. Maybe we can put in the form of a table or whatever some pros and cons, features, capabilities, in order to basically have a growing area where we can basically have material that we can use to clear our minds about the different opportunities, the different options, and what could better fit our needs, in order not to basically create a big hammer for just putting in very small sticks. Sure.
Yeah, leave that with me. I can get that updated in Confluence, no problem. Any other questions or comments or topics that anybody wants to talk about? Silence. So everybody either understood everything or nothing at all.
Martyn.
Yeah.
Hi, this is Javier from AutoCAD. I wanted to ask something. I don't know if I misunderstood. So you mentioned that, I mean, the whole point of blockchain is to ensure like, for example, in the example you mentioned, that if we have some money, that it can be traced that I'm the owner of that money. So, but then you mentioned at some point that that it's possible that that transaction won't get recorded because there is another blockchain chain that is longer, and the one in which my transaction. So is that the case? And is this something that it's solved with the oracles? Because you said that the oracles.
Yeah. So I get the question. So so I think what you're asking is like, how do we guarantee that transactions are that they 100% get into the network and consensus is formed around them? And the particular, when we were talking about Bitcoin, so obviously Bitcoin is just one implementation. It's one solves one use case for blockchain, and the approach that they take with the proof of work consensus. Now there are other consensus mechanisms, but the proof of work consensus mechanism essentially will result in a situation that what you've just described, which is you create a transaction, you propagate it to the network. The network, all the different miners will go away and they'll mine and they'll come up with various different blocks, right? And it might be that the transaction that you've created, it lands in a block, but there's another chain that comes along that's longer, that is that doesn't include your transaction, right? So as far as you're concerned, your transaction hasn't been added. So that can happen in Bitcoin. So there is miners can pick and choose which transactions they include in blocks, and they're financially incentivized to pick the ones that give them the most value at the end of it. So I mentioned earlier that the input and the output of a transaction need to add up, and if they don't add up, the change, the thing that's left over, that gets sent to a miner. So what these miners are doing is they're looking at all the transactions and they're saying, what am I going to get out of this? So if the input and output is 100% the same, then the miner's not really that incentivized to include your transaction, and your transaction just might never make it into a block. So you might be sat there waiting indefinitely and it just gets ignored. So yes, that can definitely happen in the proof of work system. The way that users get around this is that they tend to add some small incentive into the transaction. Say, okay, there's a small fraction of a Bitcoin left over. Usually, what happens is that most transactions do end up in a block and they do get mined. It's just that they take a lot longer to happen. Because miners are going to pick all of the other ones first. They're going to pick up the ones that will have to give themselves the highest incentive. So yes, it can happen. It doesn't happen very often, at least in my experience. You can work around the issue by adding some incentive. The other part of the same question is that it might look as though in your system that your transaction has been added into a block, but eventually some other chain comes along later that's far longer than the chain that you can see at your point in time. So you thought your transaction was in a block and it was accepted, and actually another one comes along which doesn't have your chain in, and that's what the network conforms to. In that case, there's not really much you can do about it. It's a probabilistic consensus mechanism. So they usually say that wait until you can see a block with your transaction in, and the 6 or 7 blocks afterwards before you're sure that your transaction has made it into the network and it has been accepted. But this is just a property of the particular consensus mechanism in Bitcoin, the proof of work consensus mechanism. There are other consensus mechanisms that we can deploy in 5GZORRO. It might be just using standard practical Byzantine fault-tolerant voting algorithms like Paxos, which don't really have the same issue of having to incentivize miners and so on and so forth. But yeah, it is a valid thing that does happen, that your transaction doesn't get accepted.
So, has this anything to do with what you said about the oracle? That basically.
No, not really. No. So this is kind of a fundamental property of the network. You can think of an oracle as kind of like a layer up, in that it's sitting on top of the network. So that the oracle relies on the network already doing all of this stuff fairly. So it's really it's really down to how we configure the network to make it behave in the way that we need it to behave for our particular use case. But the oracle doesn't really help us out with that.
Oh, because I understood that you said that we send the request to the oracle, and then the oracle wait until all the blockchain is stable, and then process the request. So I was thinking that in that sense you can look until or wait until you see your transaction in the block and then see. But okay, I might be wrong.
Yeah, no. So the oracle works as a next layer up. So the oracle is really to do with that those applications that actually sit on top of the blockchain. So you can think about like the blockchain network as like your operating system, right? And all of the applications in your operating system on your Windows desktop or whatever, they rely on the operating system behaving in a certain way. And all of these smart contracts and oracles, they're basically just applications and application, in user space on your operating system. But they don't interact at that low level layer, which is just really about deciding on what is the global state at any point in time. That's all the transaction is really. It's really just a state transition, and the consensus mechanism is just really saying, right, how do we keep a distributed network in sync? In order to do that, we need some sort of consensus mechanism, so we all agree that this is the state at any particular point in time. What the oracle is doing is it's saying, because, like I mentioned earlier, because the smart contracts, when that code is executed, it's executed on every full node in the network. So each node in the network is essentially moving the global state from state 1 to state 2 by executing the contract. So the code is executed, and the result of that code is stored on chain. What the oracle is really doing in that case is it's saying, because the smart contracts can't call out to external data sources, because to do that, it would mean that nodes could easily get out of sync in terms of executing that contract code, because if you call out to a third-party service, you might get different results depending on where you are in the world. So all the oracle is doing is it's saying, right, I'm going to go out and I'm going to talk to some data, some external data source, because the smart contract needs me to. I'm going to take the results and I'm going to post those results on chain. So I'm going to create a new transaction, put the data in that transaction. Everybody in the network, using the standard, consensus mechanism, depending on how the network is configured, that data will eventually make its way into the ledger or into the blockchain. Once it's there, it can't be changed. And that means that the smart contracts can then reason about that code without the danger of creating some sort of out of sync global state between distributed nodes. I'm sorry, does that answer your question?
Yeah, thanks a lot.
Yeah. Any other questions?
More than a question, Martin, is a potential activity for the near future. Related to the oracles, are there examples of oracles which are just implemented towards something which is not basically on a contractual base? So I'm particularly thinking to oracles that could be used for example, exposing some, monitoring data or interacting with a monitoring platform. Is there anything we can look at? Any reference? Anything you developed or in the open source, something like that?
Yeah. So the I can what I'll do is I'll add some links to the Confluence, like Gino asked. But there's an open source project that's getting a lot of traction at the moment, and it's something called Chainlink. And basically, Chainlink is it's a distributed Oracle solution that has plugins for a variety of data sources. So you can, there's integrations into Swift, PayPal. You can easily configure these things to look at your own data stores, for example. This is an interesting topic of conversation because one of the issues right here is once data is on the blockchain, it's secure and it's immutable. It can't be changed, can't be tampered with, because the network will see what's happening, and as long as the network is secure, then it can't be messed around with. The problem that we have is, how do we get data onto the blockchain network, and how do we verify that that data is accurate in the first place? Because we're going from zero to putting it onto the network. So this particular technology that I'm talking about, what it does is it can it's sort of like a voting system. So it's like a distributed way to take samples of data sources and then merge them all together depending on what function you want to use. And then if 9 out of 10 people are claiming that the FX rate is 1.1, then that's probably the correct answer. But there's a bunch of research that I think we need to do around figuring out how do we get data onto the network. That isn't just standard contract data, for example. That if we're doing things like SLA enforcement, and we're going to tear up somebody's service because they haven't been hitting their SLA for the last 3 months, we need to make sure that the telemetry and the metrics that we're collecting are accurate. So it's an interesting topic of conversation. But yes, I'll put a link to the Chainlink project. Chainlink being used by Google and another load of big operators. So they seem to have cleaned up the Oracle space.
Mm-hmm. But I see this chain.link, which is a company. So did they run the company outside or as a follow-up of the community effort? Okay.
Yeah. So the there's is it Chainlink the company, or there's smart contract, or I'll find it, but there's two things associated. There's basically a spin out for the
clear.
Yeah.
Okay, I sent over the chat here the link to the Confluence page I just created for this material. It's a tech depot, and I think we will basically start filling it in with the blockchain DLTs data and the info and the data lakes for the other major thread we have. Just to mention that actually for the moment there's a very basic template there you can find, and you are free obviously to modify as you wish. Just to bring their attachments, just drag and drop for files and online resources for links to whatever is online, and whatever you deem and is something that can be shared, please put it in there, and they will basically use also for referencing when you refer to something specific of the field.
Yeah, well, I actually have a list of reading material that we use for new hires, so I'll try and get that added up there today.
Thank you very much.
Anybody else with any questions? Going once. Twice. Okay. Okay, I think we call it a day then. Thank you for joining. Apologies for the mix-up at the beginning of the call with the terms of the time zone and the calendar invite. So I'll make sure we get that organized next time. But yep, it was a